about this data set, and we went through a couple of ideas how to motivated by this data set and trying to predict this variable survive based on some of the covariates. We started, for example, looking at this discrete covariate, and we first asked what is the optimal rule if I know the joint distribution, and then we figured that out. It was the one that looked at the posterior probability of y given x, and chose the decision that maximized that posterior probability. And there were a couple of alternative versions of that. So, for example, you could form the regression function compared with the threshold. We'll see that more. And then we asked what we can do if we don't observe or we don't know the true distribution. So what we did was use training data, like the actual data that we have here, to try to do empirical estimates of the joint probabilities, the probability distribution. And from that, we could compute the conditionals and the regression function, all this stuff, and then plug it into the optimal rule, and we'd have an estimate of the optimal rule. Now, then we talked about the training versus test error, right? And we also talked about risk and generalization. So maybe, and then in this example, I mentioned, I don't know if you did the calculation by hand, but for the entire data set that we, so we had, I don't know, a training data set of 928 examples or rows or samples. We did, so this was N train. We did like go through that plugin estimator. And it turned out to be this guy that takes X, which is the sex column. If this is female, it would be 1. If X is male, it would be 0. And so then we could calculate the training error, right? And I've done this. How do you calculate the training error? Just to see if you guys follow. We apply this to the training data, for example. I don't have the training data here, but you apply it to each one of the x's there, and then compare it with the actual y. If it's not equal to 1, that would be an error. And then you average. So that would be the training error. We wrote it as training error of f hat. Okay, and I mentioned, or we discussed, that this may not be a good estimate of what? So why do we calculate the training error? What are we after? What do I really want to have? Anyone? What do you want to have? So why do I calculate the training error? What am I after? Is the training error really what I want, or just a placeholder for something that I actually want but can't have? What is yes?
The approximation of the risk.
Great. So what we want is we want the risk, like the true risk we want. So what was our risk in this case? Or what is the risk in general?
Probability that y is not equal to f(x).
Oh, that y is not equal to f of x. That's the risk that we focused on. There is a more general version, which is the expectation of the loss. So this would be y hat. So we have a loss function, we take the expectation that would be the risk. This loss function in our case, if it's 0, 1 loss, I encourage you to go back and read and double read, like triple visit this so that you get comfortable. So for the 0, 1 loss, it would be like that. Expectation turns into this probability of misclassification. This is called misclassification rate in this case. So the risk that we focused on is a particular example, which corresponds to the case where I equally weight the errors 0 to 1 and 1 to 0, and the weights are equal to 1 basically. I pay a price of 1 if I misclassify a 0 to 1 and vice versa. That would lead to this idea of misclassification rate, or the probability of misclassification, if you want, probability of. And this x and y are that goes into the calculation are a new or a generic data point that we haven't seen. That's why this is sometimes called also a generalization error. Risk or generalization error are the same for us. So this is what I want. Why can I not have this in practice? What do I need to be able to calculate this for a given f? Why can I not? Yes.
The actual result?
The actual what? They're like, what is the result that you're pointing at?
True y value.
Not the y value, no. So we need to know the true something, right? The true distribution, that's the point. So we need to know that the actual distribution p, right? X and y do not, these are like dummy variables, just generic variables drawn from p. I need to know p. For example, I need to know in this case, if you go back up, I gave you the actual joint distribution. This is what we don't know in practice, or we don't have in practice, especially if x and y become, like y might not become complicated, but if x is more complicated, this becomes more complicated. But this is what we don't have. If we had this, if you go back to the discussion of the Oracle problem, we can calculate the risk basically for any classifier. So we don't have the true distribution. Okay, that's what we lack. And so just like any other thing that we don't know, we can try to estimate it from data. And if you like followed some of the things that I mentioned, if you try to estimate it from data using those proportions or the empirical estimate, and then plug it into this, like if I replace this with hat here, where the estimate is coming from the training data, that would be equivalent to what we calculated here. So the training error is basically an estimate of this risk, where I actually calculate the probabilities, this distribution from the proportions in the training data. So if I use the proportions in the training data to estimate my p, this guy, so the same data that I used to train the classifier, I use to estimate the p that I'm going to use here to evaluate this, then that would lead to the training error. It's also this exactly, so but you can think exactly what happens if I try to, basically if I replace this p with its average. Okay, so this is replacing this p with a p hat. So this is my p hat basically. When I average over xi, yi, I'm replacing this p with this empirical average. But this empirical average is over the training data, so xi's and yi's that went into constructing f hat. Okay, so there was some issue potentially with this. If you remember, what was that? Just to reiterate so that people know, what is this a good estimate in general? Yes.
It's to underestimate the true.
Yes. Yes. So let's say it tends to be inconsistent, yeah, right? And if you deliberately try to minimize the training risk, it would be usually underestimating. If you want to be general, you can say it's inconsistent. So it's not going to be it's not going to be unbiased, and it's also not going to be consistent. Consistency means as I increase the training size, so if this grows, I hope that this would converge to what I want, which is R. The true, this is sometimes called R. I represent as R. I want it to converge to R f hat as n goes to infinity, but this is in general not true. Not in general, but sometimes true. So, and the reason is because of the dependence between the data that's used there and the classifier. Yes.
So, from last lecture, but if F is fixed, then it will converge.
Yes, that's a great point. So if F is a fixed F, then so basically, great point. For any fixed F, we have actually R hat train F converges to RF by the law of large numbers. This you can verify for yourself. I think we talked about this. If it's not clear, go back to the previous lecture. The issue here is that when I put hat here, this is not going to be true anymore, because that F hat also depends on the data. So there's dependence on the data here, and they interact with each other. It's not necessarily true. Sometimes it's true. But for any fixed F, it's true. That's a great point. So if you fix a classifier before you see your data, just come up with a classifier, and then you want to evaluate on your entire data set, it's fine. We usually don't call that training because you haven't derived your classifier from data. So there's no training going on to get your classifier. So this name might not be necessarily a good name, but in any case. So is this clear? So what did we do instead? Like if you want to get a consistent estimate, what do we do? Sorry? Split the data, or basically evaluate your classifier or this risk, empirical risk on a subset of the data or a new data set that you haven't used in constructing classifier. So if these xi's and yi's are like tilde here, I can call this the test error. Let's say a new set of data points that are not used in constructing f hat. So I'm not going to write it, but we have written it. So that's the test error. So here we have, for example, 327 data points. So this you can say is the end test. These data are not used when constructing classifier. And I can use this portion of data, which I actually got by splitting the original data. Original data was like given me as the entire batch of about, let's say 1,300 or so, or 1,400. And I split it into like basically 1/3 and 2/3 sort of, or maybe more, like 70% for training, 30% for test. And now I can evaluate my classifier on this. So exactly the same formula here, but now xi's and yi's are from the test data, not the original data. And you do this. This I think is one of your homework problems. You'll do it on your own, and then you calculate the test error turns out to be that 0.217. The training error tends to be that. And in contrast to what I said, they tend to be very close. Okay, this is an example where actually the training error, I'm not doing the calculation here, but you're going to do it on the data. So this is, this turns out to be the case. So this is what we learned actually, if you implement the empirical rule on the training data, this is what you get. And then you apply it to the same data, you get a training error, which is close to the test error. There is a reason why this happens. which I may give to. So this is an example where actually the training error is consistent. But maybe later, so I don't want you to get confused. This is not always true. But I just want you to have it in mind that it could happen that the training error is actually a good estimate. And you might think about why this happens. And maybe we'll see examples later that this doesn't happen, which is the more common case. And then maybe we'll come back and see why in this particular case, it turned out that the training and tests are very close. Okay, so distinction of training error, test error, generalization, risk, these are clear, right? So you can say all that we're doing is trying to approximate or estimate the risk or generalization error, and the test error is like a consistent or like unbiased, also both unbiased and consistent way of doing it. Training error calculation is not a consistent way, and it's also not unbiased. Sometimes it turns out to be consistent. That sometimes remains to be seen. Okay. Good. Questions? Then we moved on. This is all like, I think, what we did last time. No questions. Then we moved on to adding more features. So now I wanted to add P-class, passenger class, like 1, 2, 3. And then everything that we did extends to this case. We saw that you can treat the new X as like a vector, like male 1, male 2, male 3, but you can treat it as a new discrete covariate with 6 levels, right? These are the 6 levels. So this is the Cartesian product, and I get these 6 levels, right? So it's not like it's not even, you can treat it as a single covariate. Whenever you have multiple categorical variables with finite range, it's as if you can treat it as a single discrete variable, but with the levels being the product of the number of levels of each. In this case, we have a 6-level feature. It's a more complicated feature. It brings more information, but I can just treat it as I had before. Okay, so now if I want to implement a plug-in rule, what should I do? Anyone? How do we implement the decision rule? Like we had the optimal rule. The optimal rules are still going to be f star. This new x is 1 if eta x is bigger than 1/2, 0 if eta x is less than 1/2. And then I can get a plug-in rule by forming a proper estimate, right, of this regression function. Eta x is probability of y equal 1 given x equal x. So how do we proceed? Let's say I give you the data. How should we go about implementing that rule? Let's see if you guys are. Right, but I mentioned you can treat this as just one covariate. Okay, what is equivalent? So how do we do it? You form a table of joint probabilities so that it can do like y is 0, 1, and then this new x is like male 1 or male 1, male 2, male 3, female 1, female 2, female 3. These are the levels, and you can fill it up. So what fraction of the data points are 0 and male 1 and so on. That gives you the joint. And then from the joint, you can calculate the conditional probabilities, right? Another way to do it is, if you recall, we can like do conditional estimate of the conditional probabilities directly. How do we do it like directly? So let's say I want to calculate the probability that y is equal to 1, given that this new x is M3, for example. How do I calculate this directly without calculating the joint from the data?
You take a subset where X is equal to M3.
Yes, exactly. So you take the subset of the data where this new like concatenated covariate is M3. So there's all these lines, not this one, right? And then within that we do what? Yeah, and then it counts. There are two, so you get 2 out of 1, 2, 3, 4, 5, 6, 7, 8. Right, 2/8, which is 1/4, right? So you get 2/8, 1/4. Is this bigger than 1 or 1/2 or less than 1/2? 0.25 less than 1/2. So what's the decision? 0. So our estimate, this is going to be our estimate. And you can do the same for example, male 2. What would be male 2? He had so less than 1/2. So f hat of M3 would be 0. So p hat y equal 1 given x equal M2, what would it be? There's just one example here, would be 0, less than 1/2, still with 0. Right, p hat y equal 1, f, let's say 3. What would it be? There are 2 cases, right? One is 1, the other one, so it's going to be 1/2, right? So regard like the boundary of it. So decision, what would be the decision? So I guess someone hasn't returned, someone had an extension. So I'm not gonna say what the decision is. Maybe later. Yeah. So this is the decision marker. So but you get that point, right? It's like exactly the same thing. Yes.
What about the other case, like M1 or M2? We don't have them in our training list.
That's great. So what would happen? So in this case, he had what? X equal
M1.
M1. So if we have just this test 10, you don't have any examples. So what should we do? You tell me, what should I do? That's a very good question. There's not enough data to actually estimate this. Yes.
Since you don't have the data, the classifier wouldn't know to do with this, so let the classifier not put anything on it, or just-
This is a great answer. So the classifier doesn't know what it should do, because we don't know, we don't have any estimate of this. So either you say, I don't know. Some people like have classifiers that have I don't know, which is a good thing to implement in practice. Usually you don't do it, but it's good to have like 0, 1, I don't know, like insufficient information. That's one way to do it really good in practice. Doesn't fit within the decision theoretic framework, right? But practically speaking, that's what you should do. I need more information. There are other ways that this happens, and we'll see. If you're willing to assume something about the structure of the X space, hopefully we'll see today. You could borrow information from other cases, but yeah.
People represents and how are you going from like male and female to F1 and to?
It represents another covariance, another feature that has 3 levels. Exactly what it means, you can check out. I think it's like they had like grades for the kind of rooms. Like one is like the first class, second class, third class, something like that, or vice versa. But it doesn't matter, but it's just a categorical value that takes 3 values. And now I want to classify based on both sex and P class. So I can treat this as a new covariate with 6 levels. Each example has a sex and a P class value that I can concatenate, treat as a new value. Okay. Yeah. This is a good question. Keep it in mind. This will seriously come up when we go to continuous cases, but at least if you also go back to our this rule that I wrote here, this is the formal way of doing it. What you get is 0 divided by 0, so you can treat it as undefined. Okay, the way we formalize this is only be defined if the denominator is non-zero. If it's 0, the top has to be 0, you can verify, and then this would be undefined. So we really don't have anything. The way at least we approach the problem so far is undefined or unknown. Yes.
Choose something randomly, for instance.
Yes.
0, and then in test error, we can check if it's okay.
You can always do random choice, but it doesn't necessarily mean that.
I mean, in the practice, they do this thing.
Let's say we'll see a little bit more, but at least in this particular case, the best thing to do is to say, I don't know. If you do randomly and look at the test, you can't go back and update your classifier. You should never use the test to update your classifier. You just can evaluate. If you use your test to evaluate and then modify your classifier, it's part of your training again. So you lose that independence. So you can always evaluate, and it's actually, you're going to see in a homework problem exactly this, that you choose, for example, you could choose randomly, or you can just output 0 or 1. It really shouldn't matter much, because you don't have any information ahead of time. You don't know really. One might be better than the other, but you don't know yet. You might get lucky, like you might also get unlucky. Okay. There's going to be one would be better than the other, right? But there's no basis to choose one or the other. Yeah. Specifically, if you look at your training area, you can decide. That's what you have, and training error is not good enough. Test error might give you. In this case, actually, you have a lot more data. So fortunately, if you do this, so you can actually calculate this. You can also do, because you have the data now, you can do and calculate the disjoint distribution, and there's enough information to like estimate each one. Whether each one is good or not depends. So for some levels, you might have very few data. For some, you might have more data. So this is where statistic matters a little bit. So there's like an error, like a confidence interval. Some of them might be very accurate, some might not be. So this may or may not be accurate. So it might be that you didn't see much, or it might be that really is 0.001. You can verify this because if you go there, you can know based on what sample size each one is calculated, what fraction of data was like M1 and 1, and so on. Sorry, not M1 and 1, but yeah, so what fraction relative to the total? So the total gives you, the N gives you, the sample size gives you the confidence. We'll see that a little bit of this later. But if you have this, you can like compute the joint distribution. If you have like an estimate of joint distribution, we can compute the conditional probability of y equal 1 given x equal anything you want. Let's say if I want to do, let's say I give you, like we calculated this, how can I, for example, calculate, which one did we not have here? Let's do that. Which one was M? M1, for example, was missing, right? Okay, so let's do M1. How can I calculate this from this estimated joint? Basic probability check.
Divided by
0.091, but this would be y equals 0. Maybe this one,
divided by some
probability y equal 1, x equal m1 divided by, which is 0.049, divided by what?
margin.
Marginal distribution of x. Not, yeah, probability of m1 under the marginal distribution of x, which is, how do you calculate that? Marginal of m1 would be some of these two, right? 0.091, 0.049, which would be, someone calculates this, please. .049 divided by
It's about 0.61.
0.61.
So
Okay. So what would be the decision here?
that's one.
Why?
It's bigger than that one.
It's bigger than 1/2, then it would be that our plug-in rule at M1 is 1. Is this correct? Or some people don't look happy? I actually have the solution on the next slide. But let's do another one. P y equal 1 given x equal, let's do one of the f's. F1, what would that be? Someone else maybe tells me what this is, like how to calculate this. What would it be? Fine, okay, other people. Someone else wants to tell me how should I write this? Yes,
The same way as the previous one.
okay,
Probability of y is equal to 1, x equals to f1.
probability of y equal 1, x equal to f1 divided by probability of x equal to f1, which is
102 over 0.001 plus 0.102,
right,
which is roughly 1.
roughly 1, but exactly what? Anyone calculate this? 99. Okay, it's a very certain decision. So what should our decision be? Bigger than 1/2, definitely. So f hat f1, this f is like the level. This should be 1 as well, right? They can do, yes.
It's might be getting into more complicated things, but if the options were 0, 1, 2, would the thing that we're judging against be 1/3?
You're talking about 2 here, or
Yeah, for y, would the then 0.99 be compared to 1/3? Maybe that's getting ahead of ourselves.
that's, yeah, getting
Okay,
a lot ahead, but that's great. So let's say I had, so this would be not binary classification, would be like multi-class classification. But how should we do that? You already know the optimal rule. Let's see if people can figure this out. So we had like 3 levels of response, 0, 1, 2, maybe they survived and they did something great, let's say. That's level 2. So yes,
Say about the first one.
Okay.
Become 0.3.
0.3.
32. and the last square come.
Okay. Good, 1/2, less than 1/2, no problem. I still have some time because I have the numbers on the next slide, so you can correct. Okay. So how should we do that? It's a very good question. If you had, if, let me do it with another. If y took values in 1, 2, 3, or sorry, 0, we had another level. So this could happen in a lot happens in machine learning. You want to classify between a lot more than 2. For example, you want to classify images, cats, dogs, like what else? Bird, like that. Like there's this ImageNet that has 1,000 categories. So it's like 1,000 classification problem. So yes.
Since I mean, you're just trying to find the argmax to maximize the probability of the class. So could you just compute the probability for each element like 0, 1, and 2, and choose maximum probability?
That's great. Yes, that's exactly what we had. So remember, there was one more step before getting to that thresholding. So this was the structure of the optimal rule. So this would be, I'm going to look at all the decisions and then find the maximum, and then that would be my f hat of x. Right. So what you would have to do is to have, you have to, the thing wouldn't be that easy, right? Because you can't say we can just compare with 1/3, right? So you have 3 numbers and they sum to 1. So it's like P y equal 1, sorry, 0, 1, 2. You have this plus P y equal 1, like, sorry, 0. Okay, let me call this like this. So P, say alpha I is probability of y equal I given x, for I equals 0, 1, and 2. I know that alpha 0 plus alpha 1 plus alpha 2 is equal to 1. The reason why we could do the comparison with 1/2 is that in the case of 2, this 1 is 1 minus the other. But in this case, you have that. It's not so easy. So I can say, I can pairwise compare them. We can decide how many you need to compare. The easiest way is to calculate them, and then you don't need one of them. You can remove one of them because of this constraint, but you at least need to keep 2 and then decide. You can still decide, right? Compute the probabilities and decide which one is the biggest. Yes.
So in this case, there's no definite decision boundary.
There's no definite decision. There is a decision boundary, which is like this being equal to 1/2. But what do you mean by there is no definite?
Multi-class classification.
Oh, that's a great question. So in the multi-class classification, is there a decision boundary?
Yeah, there are 2 decision boundary in this case.
2 decision boundaries. What would
Because we need to compare one with the rest and then with the rest.
Right, the situation would be a little bit more complicated. Like you have 3 numbers, it could be that all of them are equal. Or it could be that 2 of them are equal that are bigger than the 3rd one. So you have decision boundaries and more than, like, you can say everything together is a decision boundary, but there is decision boundaries and situations more complicated, right? You could have like a case for which alpha 0 plus alpha 1, but alpha 0 is equal to alpha 1 is equal to alpha 2. Or you could be the case that alpha 0 is equal to alpha 1 and both are bigger than. So this could happen. This could also happen, bigger than alpha 2, right? Or it could be like alpha 0 is equal to alpha 2 bigger than alpha 1, and so on, right? There's another case. So things could be, all of these are decision boundaries. You have to decide. You can't here decide between these 2, you have an issue, right? This is bigger than this, so 1 is definitely ruled out, but between 0 and 2, what should I pick? You're back at the issue. Yes.
Is it similar to like, we have 3 clusters and we have a hyperplane to like separate them?
Yeah, so those decision boundaries would look like that. It's not clustering, it's classification, but it's related. So maybe we'll see that. So if for example, think of these as functions, what you get is so this is going to define, because these are functions of x. So if you really want to write it, this is a function of x, each one. So these are really equations in x. So this gives you 2 equations. So this is equal to that, and this is equal to that. One of them is redundant. Once 2 of them are equal, like this is equal to this, and this is equal to this is enough. So it gives you 2 sets of equations. They could be hyperplanes, they could be like nonlinear functions, but 2 sets of equations, you can plot them. It's like a set of x's that satisfy that defines. In this case, things are simple because x is discrete. We'll see in the continuous case, the decision boundaries turn out to be like geometric shapes. Yes.
I'm just curious, so here we have like a multi-class situation.
Yeah.
Could you think like about like a two-class situation if you say, okay, like alpha naught is 1, and then alpha 1 and alpha
Right.
2 are another one. Is that threshold?
Yes.
We go down to-
That's exactly something that you could do. You could treat a multi-class classification as a bunch of binary classifications, like one versus the other. Right? I can try to classify 0 against these 2. Right? This is one binary classification, and I can also try to like classify this against these 2. If you want to go down, you want to do it recursively, like this against that, and then within this you can decide that's also doable, right? The thing that people sometimes do in practice is what I mentioned, one versus the other for each one. So you do basically n different binary classification, and then you somehow combine them. But this one you can also do, but the quality would be influenced. So if you do it recursively, the first is split this versus this is okay, but within this, you already are using this, you're assuming that this is good, right? So progressively, sort of when you do recursively, the quality of this classification would be influenced by the previous step. So it's actually an interesting question whether you can recover the optimal rule by a procedure like this. Maybe I should assign this as like a homework problem. I actually don't know the answer, whether you can write but it's worth thinking about. So can you implement the optimal rule as a sequence of binary classification rules in the multi-class classification? Maybe it's possible, maybe it's not. Okay, great question. But they do this in practice. One, forgot what it's called. There's a name to it, but one class against like cat versus not cat. You do it once. Dog versus not dog. And okay, that's good. Any other questions? This was a nice tangent. Gives me a lot of ideas to assign homework problems. Okay, other questions? Okay, so everyone is probably like now comfortable. So you can calculate everything, and then we can formally, or not formally, but summarize this in a decision tree. So if you remember, up to this point was a decision tree that we had. Now you can complete this, and you can say, I'm going to go all the way. If you just look at this for these, the leaves are actually giving you the information that the optimal rule has, or the plug-in optimal rule has. So for example, so these are the middle probabilities here. These are probabilities of, for example, this is probability of y equal 1 given x equal to m3. This is probability of y equal 1 given m equal to this one. Oh, sorry, this is 1. Let's do this. So this is probability of, which one did we calculate? Yeah, so probability of y equal 1 given x is equal to m1. which turns out to be like slightly, like sort of close. So 35. And so the decision, the top one is the decision. So 1, because it's less than 1/2, our decision is 0. Here it's like 0.15, less than 1/2, our decision is 0. Similar here for this one, y equal 1 f1. That's here. So you can see 0.99 is what we calculated. That's the this one is the probability of y is equal to 1, given that x is equal to f1 and decision is 1. The middle point, this is how like usually like the decision tree is fitted. This is using this R-part package, and usually you split. You do binary splits. So I had to force it to produce this. We can check. We try to use this R-part to try to fit this, and it's going to stop. It's actually going to stop. I'll encourage you to go do this. I think I have the code, a version of the code in the appendix of chapter 1. You can play with this without like manipulating the parameters. The default parameters does not produce this. If I try to fit a classifier to y based on sex and p-class, it does something else. But this is the whole picture. So if I wanted to do the sort of estimate of the plugin rule, that's what it is. Okay, so my decision would be 0, 0, 0. Basically, in the case of a male, the decision didn't change. If you recall, this is also shows you the previous one. Up to this point, you can see if you're male, decision is 0. We went down further, and still decision is 0. So this didn't change anything really. And in the case of a female, it was 1. But now, if we go to the p-class, now we have 0 here and 1 here. So there's like a little bit of information that we have now that allows you to classify this better. And based on this, you can actually calculate the training error based on the proportion as well. So anyone remember what the paired number is here? 10%, 8%. And the fraction of the points that landed there. So what is like, yeah. Those are the marginals. So yeah, this is like the estimated conditionals. This is like the marginal estimate of the marginal probability of x is equal to f1. Right. Given this information, based on this line, you should be able to calculate an estimate of the training error. Do it for yourself. And then you can compare with the training error that we had for the classifier that used just sex and see whether the training error is better or not. Okay. But in the training, you can calculate the training error and you can compare them. Okay, so you can calculate the training error and you can weigh different models, whether this is better or the previous one. We'll do a little bit of that now. But is this sort of clear? Everyone is happy with this? What this information it brings? So anyone can tell me, for example, what this number is? Let's see if people understand. Something in the middle. What is this number? So for example, this number is a probability hat estimate of the probability of y equal 1 given that x is f1, which means female and class 1. This one, for example, the probability p hat is also p hat. Y equal 1 given that x is male and class 1, p class 1. So now what is this number? Just to see what you guys think it should be.
So the probability one might be more given that. So you have comes with F1 and F2.
Given that what?
Like both F1 and F2.
Okay, so I would say this is the probability that x is either f1 or f2. So it's the probability of this event. X belongs to this. So you're not distinguishing between f1 and f2. X is female. Take the example is female, but it's either class 1 or 2. We don't know which one. That's that probability. is a valid event. Right. Okay. And you can see this classifier can be simplified. I didn't need to split. This is sort of called a split in the language of decision tree. So I split based on sex first. And then I split based on P class. And here it splits based on this being 3 or 1 and 2. And then later it splits into 1 and 2. But you can see that this decision here, this doesn't really tell me much. Right, because the decision is going to be 1 in both cases. So I could have stopped here. I don't really need to discriminate between 1 and 2. If someone is female and the class is 1 or 2, my decision is the same. So I'm going to stop here. In this case, the decision is different, so I'm going to go there. And in this case, where should I stop? All of them are 0, so I don't need this. I can stop here, but this is also the same as this. I can just ignore this. I can stop just there. My decision didn't kind of. So this decision tree simplifies, has more information, but as far as the decision rule goes, the decision rule can be simplified to something like this. We could work with this decision tree, has the same rule. If the sex is male, your decision is 0. If the sex is female, if you're in class 1 or 2, your decision is 1. If you're in class 3, your decision is 0. That's exactly the same decision rule. Hopefully people understand, right? Because at the end of the day, these are all the same, and these two are the same. So you can just summarize. So you can see I'm stopping at this point here. So that's my. Okay. Good. Everyone happy with this? So if we want to state this is saying f of x is going to be 0 if x is m1. It's 0 if x is, or let's say do back to the two variables. X1 is m, x2 is 1, x2 is the P class, x1 is female, x2 is, let's say 3, and x1 is female and x2 is either 1 or 2. That would be 1. Okay, that's the decision rule. It's a little bit more complicated. So I'm going to call this f hat 2. F hat 1 was the one that did it based on the sex. So this, you can think of that the classifier is actually based on x, which is x1, x2. Now I'm like using it like that. The original one is also based on x1 and x2, but doesn't use the x2, for example. You can say this the original one that we had, which was 0 if x1 is male, 1 if x1 is female. So it just discriminates between based on the sex. And you can think of it as that classifier, which is just this part, is also using the two features, but ignores the second feature, right? That was my original classifier. Now I'm thinking of both as classifiers based on x1 and x2. One is just ignoring this, like doesn't care about the second one. Yeah.
So for our F2, for 0, x1 equals male, x2, isn't that 1, 2, and 3?
Oh, right. I should drop this. X1 is male. I don't care about x2. Yes. Yeah, because right, this is the correct one. Thank you. Yeah, for if x1 is male, I ignore x2 because 1, 2, 3 is just everything. The other one, x1. Thank you. That's very fine. So you can see that they're the same for the male, right? For the female, this is a little bit more complicated. Okay. Now we have two classifiers. How do I compare them? Which one is better? Should I choose this or should I choose that? We can actually calculate the training errors, right? As I mentioned, you should be able to do it. The training error for the previous one we calculated, right? This was the training and test was, this was training this is for F1, F hat 1. Training error, this is test error. Okay, 0.221, 0.2117. For this one, if you can calculate the training error based on the information I gave you, which would be 0.219. So versus 0.22, was that 221 or yeah, 221. For F hat 1. And this was for F hat 1 was 0.17, 2117. So this is the test error. I'm not giving you, from this information, you can't calculate the test error, but as soon as you have the data, you can apply this to your test error and again, evaluate the test error. So the test error is slightly less. The training error is also less. Test error is more or less, or lower than the other one. So which one should we choose? If you decide based on so you want these errors to be smaller. So you go with the model that has smaller, let's say training error. Or if you really want, you could do with test error. So if I want to choose between, you shouldn't choose between based on the test error. If you really want to use test error so that's the thing that we are deciding here is called model selection. So you have two models you want to select. You can select a model based on the test error, but that wouldn't be really the test error. So if you want to do model selection, what people do in practice is they split the data into 3 parts. So you have training, and then you have really the test that in the end you want to decide, and then you split your training into 2 parts, which is training, and then there's this validation, which I'm calling test here. So I don't have like a final test, but usually you do training and test, and then you split this further into, actually this is not training, but like test and then split it into training and validation, they call it. Which is not like a test, but so you train on this, you validate for yourself on this, for example, to pick the model. Because once you use your test or whatever data to choose the models, you're essentially training on that part as well. Because model selection is a form of training. I'm gonna like choose this. You introduce dependence. So what you do is split into 3 parts: test, train, validation, test. You train this. This validation is really a test, but for your own, before even going out into the world and just declaring it or giving it to other people. You validate it as your own test, and then once you settle, there is a decision rule. You output it to someone. They test it for you. You don't go back and fiddle with it anymore. But for simplicity, I'm gonna do test here. I'm not gonna do validation test. But remember this is important in practice, okay? Because we don't have a further, I don't want to like submit it to some competition or real world and then they would evaluate it. I'll come back to this later, but let's say the test for now is a good measure. It's like unbiased, consistent estimate of the performance, and the test error is smaller for my the second classifier than the first one, right? So which one should we choose? Forget about this like little side note. Going back to what we talked about, test error is a good measure of risk, right? Like unbiased, hopefully consistent if you have enough data. And my test error is smaller than this, so should I go with this or? Yes.
I feel like given the fact that there's very small difference between the very small difference in errors between those 2 classifications. So would we choose a simpler classifier?
So what's your name?
Olivia.
Olivia. So you have a statistician in you. Yeah, that's what a statistician would reason, right? So if you're a machine learning person, you go with this, even if the distance like 0.2.11111 versus like 1 here at the 10th point. You say, oh, I beat it, like leaderboard, like on top. I won, give me the prize. That's what you do if you're a machine learning person. You see like these leaderboards, they're very like tiny differences. If you're a statistician, you'd ask, oh, maybe this difference is not sort of significant, right? Statistically significant, or that this difference is not that much. So maybe you go with the simpler model. That part, I think that's statistical reasoning. Okay. See how many people are like your first instinct is declare this is better than that. How many people are like, okay, so you're a machine learning person. How many people first instinct is, oh, the difference is not, I don't know, maybe this is not. Olivia and some other people. Okay, so you're a statistician. Both are fine. So, but depends on how you view things. But I just want to argue that our first instinct is like, we did the test. The test is sort of unbiased, cool. It seems like we're good. The statistician would worry a little bit. I just want to introduce that little worry. You can ignore that little worry and go on with your life. Nothing would probably be problematic. And but if you worry about it, I just want to give you a little bit more. Okay. So should we really say that this is really better than this? Okay. So how do we decide whether this small difference is small or not? Right. So the machine learning sort of approach would be good if this was the actual risk. Okay, so if this was the risk, and the true risk would be less than this, I would go with this model, even if it's more complex. Because at this point, it's a little bit philosophical. So if you care about decision theory, if you only care about the risk, simplicity is not a criteria, right? You only care about the risk, that's what we said, then this would be the better choice, assuming that this was the true risk. If you want to incorporate the simplicity, you have to like penalize somehow. So you have to incorporate it into your decision. We haven't done this, okay? But the statisticians are biased towards simpler model. Machine learning people are not biased towards simpler model. The more complicated it is, as long as you get the test error down, I don't care like how complex it is, let's do it. But so I just want to say that there is this complexity versus simplicity, okay, which doesn't come into our consideration. Let's say if we put our machine learning hat, right, and care about the true risk. If this was a true risk, and if you're a machine learning person, you go with this. If you're a machine learning interpretable, like philosophy, you care about interpretable machine learning, you go with try to like incorporate the simpler model. So there's like ML people, ML interpretable. This is not like, yeah, this is like a joke, but stat people. So these guys think similar, like pure ML, they don't care about simplicity, just to give you some idea. You care about only, so this is closer to actually decision theory, but this is closer to like, I want understanding, I want simplicity. Yes.
So with regular, especially
Yes.
in real life, how would you do because you would need the distributions of the risk, right, to do like a hypothesis testing.
Great. Yeah, so that's what we're getting. So if there was a true risk, then we would, I want to say the decision is not, if you care about, let's say if it was a true risk, the decision would be whether you care about simplicity or not, based on your own preference. We haven't set up the problem to account or penalize complexity. So if you care about the risk, then you go with this. But the problem is that this is in practice, and this is not the true risk. This is our estimate of the true risk. This is where the statistics comes in. Maybe the actual risk is actually higher than this. How do I know? This is a random draw. Like I have a test data which has 325 samples in it. And there is a randomness. So there is some error bars around this. There's some error bars around this, and maybe the actual risks are flipped. Now I can do some statistical analysis. Right? If you have seen the statistic, if the sample size is this, what I'm doing is like averaging a bunch of Bernoulli variables. These are binary variables that have this many, so you can evaluate the variance, how confident we are, and then we can compare. Does that make sense? So there's a serious issue, even if you're a machine learning person. Even if you care only about the risk, like pure machine learning, let's say not everyone in machine learning. This is not the actual risk, so you have to worry a little bit about this. Okay, there is a sample size attached to it, so you have to think whether this is actually the true risk. So you don't know the distribution. One way, again, if you don't know statistics, what is, let's say I don't know any statistics, how can I measure my confidence or variability of this? What can we do? Yes.
Do it many times. And then.
Right. So let's say I take a bunch of my data as training, I train on that, and pick a big portion as the test. I randomly sample from the test, right? And then the issue is that would change the sample size of the test. But the idea is that let's say if I give you a machine that generates this many test points every time you want, so you can query multiple times and evaluate this multiple times, you get different numbers and you get a distribution for the risk, like for the, not the risk, your estimate. And then the same in this case, and then you can compare, right? You can get the estimate of or the distribution, like empirical distribution for your risk if you can repeat the test multiple times, right? Because we're out of time. Next time when we come back and tell you a little bit about, you already know, hopefully if you haven't taken any statistics, you know how to test this without doing the empirical thing. The empirical thing is good, but based on this information, you can do a simple statistical test to convince yourself whether this is significant or not. Okay, but that's one way of doing it. You could do repeated tests and get an empirical distribution of your error. Okay, good. This is a good place to stop. Think maybe for yourself, think about how to do this test. How can I test whether this is significantly small? Thank you guys, and